Welcome to this presentation on OGC TB15 results regarding data-centric security. This presentation was given in the Security Domain Working Group session during the November 2019 Technical Committee meetings. The OGC TB15 project was executed between April and November 2019. My name is Andreas Matheus and I represent Secure Dimensions in TB15. The approach of data-centric security is a very broad topic. During TB15, one particular objective was studied. Is it possible to apply certain NATO standards to geospatial features leveraging OGC API for features and OGC encoding standards like GML? The results to this question are discussed in the public engineering report published under the OGC number 19-016R1. The following presentation focuses on the implementation results. In a nutshell, STANAG 4774 describes data object metadata and 4778 defines an XML structure for representing containers of metadata plus data objects. It is possible to encrypt the metadata and the data object with different keys, which allows the separation of concerns and selected confidentiality. Two different architecture alternatives have been implemented to test the combined use of NATO standards with OGC API features and feature collections containing GML encoded features. The first approach, from feature collection to STANAG, represents the ability to upgrade an existing OGC web feature service to STANAG encoded, encrypted and signed XML data representations. The second approach, STANAG containers inside a feature collection, demonstrate the ability to request a feature collection from a stenickaware feature service via the OGC API for features. The response here is a digitally signed feature collection where each member is a STANAG 4778 encoded data object. For applying information flow control based on our clearance and data classification, the first approach uses the feature type as a classification. The second approach is based on actual metadata associated with each data object. Both approaches are implemented based on the same security components provided by Secure Dimensions, the GeoPEP and the GeoPDP. As illustrated on the previous slide, the GeoPEP acts as an interceptor for both approaches. It exposes the OGC API features with the extension of an access token. The access token submitted with each request represents the acting user. The GeoPEP fetches the user claims, clearance and public key from the user management system via OpenID Connect. The further processing of the intercepted request and response depends on the authorization decision returned by the GeoPDP. In fact, the processing for the different approaches is controlled by different XAML3 and GeoXAML policies, loaded by the GeoPDP. To accommodate the required data-centric security-related functions, two new obligation handlers got implemented during TB15, XML digital signatures and XML encryption. To ensure maximum flexibility, the GeoPEP is available as an Apache web server module. Depending on the deployment plan, the module can be directly loaded into the web server that hosts the OGC API features or loaded with an Apache reverse proxy setup. For alternative 1, the module is directly loaded into the web server that hosts the LD proxy and the Geo server. For the second approach, the reverse proxy setup is used. More information on the implementations can be found on GitHub. For demonstrating the ability to apply access and information flow control based on user clearance and feature classification, some demo users with fictitious clearance are available. Also, some feature types of a standard GeoServer deployment are associated with a classification. Enforcing the information flow control of confidentiality, no read up, no write down, for read access, a user's clearance must be at least equivalent to the data object's classification. The bottom table illustrates the results of read access for the different users and feature types. Managing deviations from the static information flow control is important when it is relevant to dynamically adopt access. This can be important to better manage a disaster by defining a time window and an access area. For example, access during a specific time and for users located within the policy area have access to all data regardless of their clearance. As the user is not aware that the system is giving additional access to feature types that are denied under the static control, the original classification of the features is obfuscated. So instead of returning a real classification of the data object, the GeoPEP obfuscates it to NA. For demonstrating the spatial part of the policy area is set to a rectangle in Midtown Manhattan, which is south of Central Park. The actual demonstration now is split into two simple activities. The first, the client must obtain an access token representing the acting user. Second, the access token is submitted with the request to the DCS-enabled OGC API features endpoint. An access token can be obtained via CURL or a simplistic app provided for TB15. The example results for user Jane and Joe simply reflect their ability to obtain a top-secret feature. Jane can fetch the features as her clearance is top secret. This is illustrated on the left. Joe cannot fetch the features as his clearance is unclassified. This is illustrated on the right. Demonstrating the access based on the spatiotemporal policy is triggered by submitting an additional parameter with the request, subject location. There is no extra parameter for the time as the GeoPEP uses the system time. The screenshots illustrate the difference when requesting access to features under the normal and spatiotemporal access. As shown on the left, Jane can fetch features north of Central Park. As shown on the right, triggered by spatiotemporal policy by submitting a subject location parameter reduces the features to the area defined in the policy. As a result, the feature north of Central Park is missing. The user Joe has clearance of unclassified and can therefore not fetch features of type Tiger Roads as they are marked classified. The left figure illustrates the response that does not contain any features. The right figure illustrates the response when triggering the spatiotemporal policy. The response includes the features inside the policy area, but the metadata labels for the classification are NA. The responses for Joe acting outside the temporal condition are identical. No features returned. For the implementation of Alternative 3, a stenickaware feature service provides different satellite images. For demonstration purposes, the Landsat 8 B3 images are considered top secret. With this classification, only Jane is able to fetch the data. As illustrated to the left, Joe receives an empty feature collection. As illustrated to the right, Jane receives a feature collection where the feature is a STANAC encoded data object including STANAC metadata and an encrypted data object. The GeoPEP is able to filter based on the metadata part of the DCS container. This illustration presents the structure of the created feature collection again in more detail. Similar to STANAC 4778 encoding structure, the feature collection includes an XML digital signature. Even though this is valid XML, it breaks the schema for the feature collection structure. The conclusion of the data-centric security work in TB15 is that it is possible to combine the NATO STANACs 4774 and 4778 with OGC feature collection and GML encoding to achieve data-centric security. But the XML digital signature in the feature collection breaks the associated schema. To reflect this fact, a change request was created. For more details on the result, please observe the Data-Centric Security Engineering report published as OGC 19-016 R1. Thank you very much for listening.